Now we're going to look at comparisons between different triangles, specifically what we call similar triangles. With similar triangles, you have all corresponding angles that are congruent. Basically, you have triangles that are the same basic shape but different sizes. One is bigger than the other essentially, but all the angles, corresponding angles are the same. So in my two triangles here, I have triangle ABC and triangle XYZ. The corresponding angles A and X are the same measure, or have the same measure. B and Y have the same measure. C and Z have the same measure, so they're congruent accordingly. And so the way that we represent that, just notationally on the pictures here, is that we draw an arc on the corresponding angles and put a little tick mark on each one. Now, some textbooks you may have seen, maybe you put like a single arc and a double arc and a triple arc. Instead, what we're going to do is put a little tick mark on the arc. So B and Y are each going to get two little tick marks, like so. And then angle C and Z are corresponding, and so they'll get 3 tick marks. And it doesn't matter which one gets 1 versus 2 versus 3, as long as the corresponding ones have the same number. So if one of them has 1, then its corresponding angle has that 1 tick mark, that's all. But basically then, angle A is congruent to angle X, angle B is congruent to angle Y, and angle C is congruent to angle Z. All right, so that's just by definition, really, similar triangles. What's an interesting consequence of that, and I won't go through and prove it, though that could be done as well, but a consequence of that is that corresponding side lengths are proportional. Okay, and so, or we say that the ratio of corresponding sides are equal. Same idea. Basically, what we mean then is that if I have, let's say I use, instead of capital letters, for the angles I'll use lowercase letters for my sides, and I'll go opposite. So opposite angle A is side little a, angle B, little b, C, C, and then we've got X, Y, and Z. Now the X, Y, Z are hard to tell, but I'll just make them smaller. So anyway, we have those side lengths then. And so if I were to take side A over X, that's equal to B over Y, which in turn is equal to C over Z. And so the ratio, that Z looks a little big, it almost looks like capital Z, but it is not. And closer. And so these ratios between the sides are equal. If ratios are equal, then they form what's called a proportion, right? Two fractions that are the same form of proportion. And that's true for any combination of the three. And you can actually rearrange some of these. You can kind of move things around using properties of equality and end up with some other features like ratios of sides within a triangle are equal to the ratio of the corresponding sides in the other triangle. So something like A over B is equal to X over Y, for instance, and so forth, right? So you can get a lot of these combinations to be proportional so long as corresponding sides are in the same position of the triangles. But typically the one that we're going to see is this combination here, where you have one side from one triangle on top, the other side from the other triangle, the corresponding side from the other triangle on the bottom. And it doesn't matter which one's on top. You could do X over A if you wanted to. It's arbitrary. But the ratios will be the same, and you have to be consistent. So if the numerator comes from the bigger triangle on one fraction, it has to come from the bigger triangle on the other fraction as well. Okay, so that's just gives you an overview. So not only are the angles congruent, corresponding angles are congruent, but ratios of corresponding sides are equal. Okay, so that's really important for similar triangles. And so, if I threw some values in here, maybe I know some of those angle or some of those side measures, but I don't know all of them. For instance, I could make a triangle here. One interesting thing about similar triangles is if you were to take any arbitrary triangle and insert inside of it a side somewhere that's parallel to another side. So for instance, I've got a side here on the top left. If I insert somewhere along the lines a line segment that is parallel to it, I've actually formed two similar triangles. And there's ways to prove that using, corresponding angles of parallel lines cut by a transversal are always congruent. So we can get congruency here, we can get congruency here, and then of course they have a shared angle, which is obviously the same, and so we have congruency there. Okay, now if I knew some of these side lengths, let's say I know that the big triangle is maybe, I don't know, let's say 8 inches, 10 inches, and 12 inches. And then maybe I know that the smaller ones here, maybe this is 6 inches. And the question is, what are these other two small sides if I know that other one? Well, they're all going to shrink by the same rate or the same ratio, proportionally. So from 8 to 6 and 12 will go to something and 10 will go to something. And what we need to do is just figure out what those somethings are. Well, we can set up our proportions. We can say, well, 8 over 6 is, so that's long over the corresponding shorter one, is equal to the long side 12 over its corresponding, maybe instead of a question mark, I'll put like an X and a Y in there. That way there's some variables to put in there. So 12 over X, right? So long over short, corresponding sides form ratios that are equal. And then to solve this, if you know how to solve proportions, there's two ways to think about it. What I like to do is multiply both sides. Well, I guess there's two ways. I like the other one better. We're going to solve using cross multiplication. So with any proportion, you can take the opposite values and multiply them together. So you get 8x equals, and then the 6 and the 12 makes 72. So you multiply on the diagonals essentially across the equal sign. Now where does that come from? That was the other one I was going to say. Basically you multiply both sides by the denominators by 6x and then cancel things that are common. It's a little bit extra work. It gets you to the same thing. Okay, so this is just a shortcut to doing that step. Anyway, you get 8x is equal to 72, and then you solve for x. And so x is equal to 9. Okay, so I have a 9-inch side right there. Okay, that's one of them. The other one, the y, is found by doing a similar proportion. You have the 8/6 equal to 10 over y, and then you cross multiply once again. So we have 8y is equal to 60, right? 6 times 10. And then you divide out the 8. Divide out by 8, and y is going to be 60 over 8, which is the same as 30 over 4. If I reduce by 2, if I reduce again, it's 15 over 2, right? 15 over 2, or equivalently 7.5. Right, so the y is a 7.5 or 7.5 inch side, 15 over 2. Okay, So it just gives you an idea of how you can use these proportions to get the corresponding missing side lengths. We can also look at angle measures using similar triangles as well. Let's get rid of this. We can set up a set of similar triangles by having two parallel lines, kind of like I often call this like a bow tie. Two parallel lines cut by two transversals, one going this way and one going this way. And because it kind of looks like a bow tie, right, if you're looking at it on an angle. Because of the parallel lines, each of these other lines are transversals. And so we know that alternate interior angles are congruent, which means that the angle down here in the lower left is congruent to the one up on here, the upper right, because they're alternate interior angles to that transversal. Similarly here, the upper left is congruent to the lower right. And then in the middle, we have vertical angles. Well, those two angles have to be the same because they're vertical. They're congruent. So that would be 3 tick marks on those. So we have our corresponding angles. And now if I were to give you some of the angles, let's say the one in the lower left here is maybe 30 degrees, and the one on the upper upper left here is well, let's say it's 45 degrees, then we should be able to find all the other side or all the other angle measures, right? The third angle measure on the triangle on the left here is found by adding all three and equaling them up to 180, which is the same as subtracting these two given ones from 180 to find the missing, right? So 180 minus 30 is 150, and then subtract off the 45, and that would be 105 degree angle. Excuse me, 105 degree angle right there. For some reason that's not a very good drawing. It's not very much to scale, right? That doesn't look like it's over 90 degrees, but according to what I drew up here, it is. So that's 105, which means its corresponding angle is 105. So 105 degrees for both of those two. And then of course the corresponding angles, I know this one down here is going to be 45 degrees and the one up here is 30. Okay, so we can find corresponding angles and corresponding side lengths when they're missing based upon these two main properties, that the corresponding angles are congruent and ratios of corresponding sides are always equal. From there, we can even do some applications. There are some kind of neat applications that come from this. How useful they are to you, I don't know, but they're kind of interesting. If you wanted to figure out the height of an object, say the height of a building, you could use shadows and similar triangles. So you have a building here, and let's say you had a person standing over here as well. Very crude drawing, right? And the sun is at a certain angle. Let's say at a given point in time during the day, the sun is up here at a certain angle, and it creates a shadow on the ground. Now, actually, I have a bad angle to make this work. Let's say the building's height, or the building's shadow is cast down here. Oh, this is getting worse. My drawing is getting worse. Hold a second. Hold the phone here. Okay. And then I've got a person. Now, technically, the sun will be at a slightly different angle to the person, very, very slight. But for purposes of what we're going to do here, the sun will appear to be in the same angle if you moved a little bit, from a building to this person over here. the angle changes so minute it doesn't really do anything. So we're going to assume these to be parallel. And there. And so we have basically two similar triangles. We have one constructed, maybe I'll pop those in a different color so that they stand out. We have one triangle right here. And we're going to assume it to be a right triangle because I assume the building is perpendicular to the ground. Although my illustration is really not that way, as it looks like it's on a hill. Oh my goodness, from here it looks pretty parallel to the ground, to the floor. That's not very good at all. Anyway, it doesn't have to be a right angle, actually. And then I can form a right triangle here, or any triangle, doesn't matter. Again, it doesn't have to be a right triangle, they just have to be similar to each other. And so because the two rays of light here are parallel, or assumed to be parallel, we have two corresponding angles when you have parallel lines cut by a transversal. The ground is the transversal. And so these two are congruent, and then the angles here made with the ground, because the building is vertical, the person is vertical. These two angles are corresponding. And of course the angle, that means the third angle must be corresponding. It must be congruent as well. We don't even have to prove that from the diagram. We just need to know that because when you take these two angles off of 180, it'll be the same as taking these two angles off of 180. And so those last sets of angles there are going to be congruent because we know the sum is equal to 180 for each triangle. Okay, so we have our similar triangles. Now let's say you could measure the shadows. You're down here on the ground, right? You can measure the shadows. Let's say this shadow here is 4 feet for the person, and the person is 6 foot tall. Okay, just to give us some nice numbers, right? And then let's say the building here has an 80-foot shadow. The question then is how tall. We'll call that H for the height, right? How tall is that building? So we can set up a proportion because the two triangles are similar. So we can say that, for instance, 6 over 4 is equal to H over 80. And again, that's maybe even not the best. It'll work, but it doesn't fit the structure I showed you a moment ago. I should get the corresponding angles in the same fraction. So it'd be like 6 over H, the two vertical sides, equals 4 over 80, which are the two along the ground. And we don't even need to know the other side, the third side. All I'm looking for is the height of that building. And so then I again cross multiply. You could actually, before you cross multiply, you could reduce this fraction. It will actually help this to go a little bit faster. I might write this as 6 over H equals 1/20th, right? Because 4 goes into 80 20 times, so I could divide them both by 4. And then cross multiply. So H times 1 is H. 6 times 20 is 120. So it appears the height of the building is 120 feet if it has an 80-foot shadow, according to the ratio for the person, okay, to its shadow. So that works out pretty nicely. You can calculate, or at least get pretty rough estimates for things like that, distances and heights. If you are able to measure some easy ones and then use some angles, some consistent parallel line type angles to get or to determine the unknown sides. So pretty good. We just need the similar triangles out of it.